All right, let's get into it. Today we're cracking the code on one of the most elegant and, frankly, powerful algorithms out there, binary search. If you've ever had to find one thing in a massive pile of data and you need it fast, well, this is the secret sauce. So, let's dive in.
So picture this. You've got a phone book, an actual physical phone book, and it's got a million names in it. You need to find Smith. What's your first move? Are you really going to start at page 1 with Aaron and just flip every single page one after another? I mean, that could literally take all day. This is the exact kind of problem that search algorithms were born to solve.
So first things first, let's talk about that obvious page-by-page method. The one we'd all probably try first. It's the classic way to find a needle in a haystack.
Now, this method actually has a name. It's called linear search, and it's exactly what it sounds like. You start at the very beginning and you check every single item in a straight line until, hopefully, you find your target. It's super simple, it's direct, but you can probably guess it's not the smartest tool in the shed.
The process itself is dead simple, right? You pick an item, you check it, and if it's not the one, you just move on to the next one. And the great thing is, this works on any list. Doesn't matter if it's sorted or a total mess. But the bad thing, well, if that phone book has a million names and Smith is way at the back, you're in for a very, very long day.
But come on, there has to be a smarter way to do this. When we're talking about massive amounts of data, going one by one is just not going to cut it. We need a better strategy. Okay, so let's see how we can speed things up. And I mean dramatically speed things up. It's time to introduce the hero of today's explainer, the binary search algorithm. Now, I want you to pay close attention to that one word in bold right there, sorted. This is the single most important, non-negotiable rule for binary search. Your data has to be in order. The whole reason the phone book example works is because it's alphabetized, and that one simple requirement is what unlocks this incredibly powerful technique.
And this quote? It just nails the strategy. Instead of checking items one by one, you divide the problem and you conquer it piece by piece. You're not just getting rid of one wrong answer at a time, you're eliminating half of all the possibilities in a single step.
So here's how it works in practice. You take that giant phone book and you open it right to the middle. Let's say you land on Miller, but you're looking for Smith. Okay, since S comes after M in the alphabet, you know with absolute certainty that Smith is not in the entire first half of the book. Boom, you just threw out 500,000 names in one shot. Now you just take the second half, find its middle, and do it again. You just keep cutting the problem in half until you've completely zeroed in on your target. So that's the logic, and it's pretty slick, right? But how do we take this really intuitive divide and conquer idea and turn it into a set of instructions a computer can actually follow? Let's bridge that gap and take a look at how this is implemented in the C programming language.
A computer doesn't see pages, of course. It sees array indices. So to keep track of our search area, we use 3 key variables. Think of low as the bookmark for the start of the section we're looking at, high as the bookmark for the end, and mid is, well, the halfway point that we calculate every single time we loop.
Now, the real engine of this whole thing is this one loop condition. The search keeps going as long as low is less than or equal to high. This is basically the code asking, is my start bookmark still before my end bookmark? As long as the answer is yes, we have a valid section to search, but if low ever creeps past high, it means we've narrowed it down to an empty space. And the thing we're looking for, well, it just isn't there.
And here's that logic in action. We start with the whole array, right? Index 0 is low, and the very last index is high. Then, inside our loop, we calculate the middle index. We check the item there. Is it our target? Awesome, we found it, we're done. Is our target smaller? Okay, then we can ignore the entire right half. All we have to do is move our high bookmark to just before the middle. Is our target larger? We do the opposite, ignore the left half by moving our low bookmark to just after the middle. This loop is the perfect imitation of us tearing out half the phone book with every single check.
So, we've seen the logic and we've seen the code. Now for the big payoff. Just how much faster is this smarter search, really? Well, the difference isn't just big, it is absolutely staggering.
In computer science, we have this thing called Big O notation to measure how efficient an algorithm is. It's just a fancy way of describing how an algorithm's runtime grows as you give it more and more data. Linear search is what we call O of n, which means the search time grows in a straight line with the number of items. You double the items, you double the search time. But binary search, that's O of log n, or logarithmic time. And that, my friends, is a total game changer.
So what on earth does O of log n actually mean? It means that even if you double the number of items, it only takes one extra step to find what you're looking for. Let's go back to our million-name phone book. A linear search could take, in the worst case, 1,000,000 steps. A binary search will take, at most, about 20 steps. No, you heard me right, not 20,000, just 20. This incredible efficiency is why everything feels instant today, why your dictionary app finds a word before you blink, and why a database can find one customer out of millions in a flash.
This table really just lays it all out. Linear search is super flexible. It'll work on anything. But its performance, O of n, just falls off a cliff with large datasets. Binary search, on the other hand, is ridiculously fast, O of log n. But it has that one strict rule. The data has to be sorted. And, the code is a little more complex to get right. It's a classic trade-off between something being easy versus something being incredibly high performance.
So you've got these two tools in your programming toolbox now. How do you decide which one to pull out for a specific problem? The takeaway here is actually really simple. If your data set is small, or if it's all jumbled up and you can't sort it for some reason, linear search is totally fine. It'll get the job done. But the second you're dealing with a large, organized data set and speed matters, well, binary search is the champion every single time.
And that leads us to the perfect final question, doesn't it? We know binary search is blazing fast, but its power is completely dependent on having that data sorted first. So, what's the next piece of the puzzle? If you have 1,000,000 unsorted items, what's the most efficient way to get them all in order to begin with? Well, that is a whole other fascinating world of algorithms for us to explore.